Welcome back, everybody. We're going to be finishing off 1.5 and hopefully starting, and if not finishing 1.2 or 2.1. That's my, I didn't post the 2.1 notes. Oh, fire truck. Lovely. Well, it's okay. It's okay. It's not okay, but it's okay. Okay. We'll figure that one out. I have your quizzes graded and they're entered online, so I'll be passing them out during the break. But right now we'll be starting continuity of piecewise functions. I knew I was forgetting something, and I'm sorry about that. We'll figure it out. So what we talked about last time is that continuity, the way to find continuity with functions is that the functions are continuous on their domains, which is what we did last time. But piecewise functions are a special case because they exist as separate functions on separate pieces. So their domains aren't exactly what the normal domain of that function would be. So I kind of have a step-by-step procedure. Step one was to find all the discontinuities on each piece within its interval. So there are two pieces here. There is the first piece, the top piece, 10 over x plus 1 times x minus 2. And then there's the second piece, x minus 5 for x less than 0. So if you're just examining the function 10 over x plus 1 times x minus 2, then it's discontinuous at negative 1 and 2. Just examining it, just taking this function right here and ignoring it. Ignoring that function. That function, the 10 over x plus 1 over x at times x minus 2, that function has discontinuities at negative 1 and 2. However, negative 1 isn't in the interval. We're only defined as that function for values greater than or equal to 0. So x minus 1 is not a point of discontinuity because the graph is not that. Like our function f is not that function at negative 1. So we don't need to worry about it. Is that clear? Does anybody need me to explain that a different way? Yes, absolutely. Thank you. So because our function f is only equal to this equation, 10 over x plus 1 times x minus 2 for values greater than or equal to 0, that means that that place is not, like we can't, like when we try and plug in negative 1, we're going to be working with the secondary function. So we don't need to worry about it. If you're looking at the graph-wise, what this would look like is, so this function right here would look like this. So negative 1, 2, and the curve would look, so before that it's negative, which makes it positive. So it would look like this. In between that, it would be negative, so it would look like this. And then it would look like this. That's the full graph of y equals 10 over x plus 1 times x minus 2. Please don't write this. This is just for observational sake. That's what the full graph looks like. However, because we're only defined on it for greater than or equal to 0, what our graph actually looks like is we erase this portion. Wait, no, not that portion. I don't know why they got rid of certain thing about notability. So that's the piece that our function, like for f, that's all we have from 10 over x plus 1 times x minus 2. And there's only one discontinuity there, right at 2. Does that make sense? Yes, Jake.
Why is that? Because negative 1 would cancel it out.
So negative 1 is there. And that is the discontinuity of this graph. But we're only defined as this graph for values greater than or equal to 0. So we've kind of removed it because it doesn't exist there.
Right.
If it had said, so that, like, I'm thank you for asking these questions. This is important. This is an important thing to understand about piecewise functions. If instead this had said x greater than or equal to negative 5, and this is x less than negative 5. If that had been the case, then both of the values would have been discontinuities. Does everyone see that? It's a good, like, so that's just for observational purposes. But we're working with this one where specifically we're greater than or equal to 0 or less than 0. So we have one discontinuity from the first piece. Then we'll also look for x equal to, for x minus 5 on x less than 0. No issues. That's a polynomial. In particular, it's a line, but it's still a polynomial. And polynomials are defined everywhere. You can plug in whatever number you want. So the domain of a polynomial is consistent with its domain or its interval of continuity. So there's no issues. So we don't get any discontinuities from that piece. Because if you were to just draw it, once again, x minus 5 is this graph. But we're only worried about it for the left-hand side. And that's just like, regardless of where you are, it's a continuous line, but either way. So there's no issues from that second piece. That is step 1. Step 2, and once again, I know this is taking a long time, but that's because we're writing down all the procedure. And we're writing this down in perfect, like for our notes, for legibility and understanding of our notes while we're reviewing. Step 2 is going to be determine if discontinuous at dividing values. Determine if you're discontinuous at the dividing values. This function only has one dividing value at 0. But there's plenty of examples where you have multiple. In the example then, and by the way, as a reminder, continuity needs 3 things. You need the function to exist there, you need the limit to exist there, and they need to be equal, right? So, for x equals 0, that's our only dividing value. F of 0 equals, which function should I use? The top one, because that's the one that's greater than or equal to 0. So we'll plug in 0 into that, and hopefully we get a number. We will, but that's going to be 0 plus 1 times 0 minus 2. That will be -5, i.e., it exists. So we know that the function exists there. F of 0 is defined. Now we need to check the limit. Next, check limit exists. Now, because it's a dividing value, that's what we spent a good portion of 1.3 doing, is piecewise functions and one-sided limits. Because it's a dividing value, on the left-hand side of 0, it'll be one function, and on the right-hand side of 0, it will be a different function. So we need to check the left and the right-hand limits to make sure they agree. So the limits as x approaches 0 from the, what do you guys want to start with, right or left? Right side, sure. Of f of x, that'll be the limit as x approaches 0 from the right of the top piece, because that's the function that's defined for values greater than or equal to 0. So that'll be 10 over x plus 1 times x minus 2. And we can just plug in 0. There's nothing, we're not going to be dividing by 0 here. We're not going to be doing anything bad. So we can just plug it in. So that'll be 10 divided by 0 plus 1 times 0 minus 2, which would also be -5. So the right-hand limit exists. And I know we did that calculation. If it's going to be continuous there, then that calculation is going to be the same. But we still have to do it because in one context, we're talking about a function value. In the other context, we're talking about a limit. Yes, they give me the same number, but that's kind of by design.
If we gave you a different number, it would be discontinuous.
So excellent question. Louis asks an amazing question. We could actually, if this gave us 7, we could immediately stop. Because even if the limit existed, like even if we test zero, limit as x approaches 0 from the left and got -7, so one of two things would happen, right? Either you get the same number and the limit would exist, but it would be different than the first number, and therefore it would be discontinuous. Or you would get different numbers, in which case the limit didn't exist, in which case it would be discontinuous for the same reason. Let me say that one more time because I said that quickly, because this is an excellent question. If this had equaled -7, which it doesn't, it equals -5, but let's just assume that it did, then we could stop here and say it's discontinuous. And the reason we could do that is that there are two options. Either the left-hand limit exists and equals -7, in which case this fails the third condition. You need the limit and the function to be equal to each other. Or it could be that the limit exists or doesn't exist and equals a different number, in which case then the full limit doesn't exist, and that's the second condition of continuity. You need the limit to exist, the function to exist, and them to be equal. So if you didn't get a number there, if you didn't get -5 there, that would be a cause for concern. And that would mean that you're probably like that you're going to have a discontinuity. But either way, the limit as x approaches 0 from the left of f of x, that will be the limit as x approaches 0 from the left of x minus 5. And that's a polynomial. And polynomials, we can just plug in the numbers. We can just plug them in, it's fine. We're not dividing by 0, we're not taking square roots and negative numbers, so we don't have to be concerned at all. That'll be 0 minus 5 equals -5. Same z's. How do you spell same z's? Is it with a Z or an S? Okay. All right, I like having the Z. So same z's, which means that the full limit exists. The limit as x approaches 0 of f of x equals -5. Yes.
Can I ask you, when we check the limit, as x approaches 0 from the right, did we just plug in 0? Because if we can get a value 9 times out of 10, that's the limit, as opposed to like 0.1?
Yes.
Okay.
So as long as you can plug in the number, like for this class, as long as you can plug in the number, that will be the limit. I can't think of a situation where that wouldn't be true. But let's just get this out of the way. Yes, Jade.
So say instead of the right side of 0, say it was like 1, would we still just plug in 1? regardless? Okay.
Yes, because 1 is not a problem value.
Yeah.
-1 is a problem value, 2 is a problem value, but 0 doesn't cause any issues.
Okay.
So that means, so all conditions satisfied, which implies continuous at x equals 0. So that's not a point of discontinuity. Our curve actually ends up connecting to our line ends up connecting to the irrational function perfectly at 0. So we only have one discontinuity. Step 3 is to use step 1 and 2 to answer. Use step 1 and 2 to answer it. So that's why I encourage you to underline your points of discontinuity, because there's a lot of work going on here. And when that happens, if you're trying to parse through all this work, it's hard to find it. So that's why I underline it here. You can even highlight it, even on an exam, highlighting is fine. I encourage you to bring any colors that you want. Please avoid using red. Like red is an accent, yes, but do not write your exam in red. I will curse your name. So anyways, but you can use highlighters, you can use blue pens, green pens, whatever you want on an exam. Helps you do the exam better. Awesome. So use step 1 and 2 to figure out your answer. In the example, only discontinuous at x equals 2. Now the question is that the answer? Because the question can change. Some questions might ask you to find the intervals of continuity. Some might ask you to find the points of discontinuity. So this question was asking us to find the intervals of continuity. So you can use a graph, you can use a number line to figure it out for yourself. Here's 2. That point needs to be plucked out, but everything else is fair game. But as you get better with this, you don't need to do that. It's just for now. If you want to skip that step, be my guest. So the answer is that it's continuous cont on negative infinity parenthesis to 2 parenthesis union 2 to positive infinity parenthesis. Sure, we'll use a parallelogram. Y'all slanted and cool. Any questions on that? Yes. From the very first step, we found one discontinuity in the first step. Excellent question.
Because it would have been, if it wasn't a piecewise, it would have been 2 points of discontinuity negative.
Yes, but since it's a piecewise function and it wasn't defined as that function on at -1, we just got to remove it.
Why wasn't it defined at -1 again?
It's not like, so why was this function not defined at -1?
Yeah.
Yeah, because you'd be divided by 0. And so, yeah, great question. So when we go back to this polynomial, like every function we know and love, or hate in your situation, they're continuous on their domains, but piecewise functions are just the special case. So this function's domain is everything except for -1 and 2. And that's why those are the points of discontinuity, or the values of discontinuity. Yes.
So for step 2, if you hadn't gotten the same answer of -5 for both limits, would it be discontinuous at 0?
That is correct, as we will see in the next example. So this one here, this has 2 dividing values. Now, we did the whole step-by-step process and it took a full page. I'm going to show you this one's going to take less time because we're going to be doing it all at once. And so you don't need to be as clear with your writing on the exam. You don't need to, like, if you want to skip writing, for people watching the recording, you don't have to write this. You can immediately go to this. Just make sure you're certain that you're using the right piece. But a lot of those things can be done quickly. So, but anyways, this one. Find all the values where this function is discontinuous. Now, one of the things I always like to do if I have a rational function is always write the factorization later on, like next to it. So I'm going to go ahead and do that right off the bat. This thing factors to -24 over x minus 5 times x plus 3. Just because we might need it. We will definitely need it, but just, it never hurts. Even if you don't use it, you still practice your factoring, and factoring is always useful. All right, so I'm going to label it as step 1, but typically speaking, you don't need to. We're going to look at each piece separately. There's 3 pieces for y equals -24 over x minus 5 times x plus 3 on x less than -1. Because I factored it, I can immediately write the answer. Discontinuous at x equals, take a second, make sure you I'm saying for the original function, for f, what discontinuities do I have? -3 and 5, but we're gonna, so -3 and +5, but one of these can be removed. The 5. So we can cross it out and say not in interval. Or not in the piece, however you want to say it. Not in the piece, not in the interval. You don't even need to specify that to me on an exam. You can just cross it out, call it good, but that's all you need to write. You don't need to go through, like, I know you know how to solve polynomials. I know you like, you tested that in 182, or sorry, 126, 127 and before. I don't need to test that. You could just write that answer and I'm good. So there's only one discontinuity from the first piece. For y equals 2 on -1 less than x less than 4. Are there any discontinuities? Nope, because it's a polynomial. One of the most basic polynomials in the fact that it's a straight line, but it is a polynomial. So no discontinuities. And for y equals -x squared plus 26 on x greater than or equal to 4. Discontinuities at all? Nope, because it's a parabola. And parabolas are defined everywhere. Every polynomial is continuous everywhere. So there's no discontinuities there. No discontinuities.
I think I asked last time, but essentially discontinuity and domain are kind of the same thing, right? If
Yes.
in the domain, if we can't find anything outside the domain, there's no discontinuity.
That's correct. Yes. All right, that's step one, much faster than before, right? You can do it pretty quickly. You don't have to write too much. Step two, we have two dividing values. We have two dividing values. We have -1 and we have 4. So for -1, for x equals -1, let's say that for x equals -1, you're going to check to make sure that the function exists there. So what is f of -1? It's 2. Because at -1, you're the constant function 2. That's just 2, i.e. it exists. That's the first condition satisfied. For continuity, function needs to exist, limit needs to exist, and they need to be equal. So we've got the function existing there. Now we just need to check the limits. So because this is a dividing value, it'll be two different functions it'll be one function on each side, two different functions. So the limit as x approaches -1 from the right of f of x is the limit as x approaches -1 from the right of 2. Because when you're approaching -1 from the right, you're talking about numbers that are slightly larger than -1. So you're in the second piece. And the limit of a constant is the constant itself. And we'll check the limit as x approaches -1 from the left of f of x. And that's when we use the top function. So the limit as x approaches -1 from the left of -24 over x squared minus 2x minus 15. Or you can use the factored form. The only reason why I wouldn't recommend using the factored form is that that was based on our work, and we are humans. We are capable of making errors. Whereas me writing I'm not capable of errors. I'm perfect, right? And I'm very humble about it too. But in all seriousness, you could have accidentally. I saw it a couple times on the quiz where students jumbled things up a little bit wrong. They factored it incorrectly, and so if you use the factored form that you made incorrectly, unless you're extremely lucky that day, you're going to get a different number, and so you're going to find that it's discontinuous where it's not. So, anyways, let's check this out. We already know the factorization up here. -1 should not cause an issue, so we can plug it in. That'll be -24 divided by -1 squared minus 2 times -1 minus 15. That will be equal to 24 over -15, -12. So -24 over -12, which is +2. So the limit as x approaches -1 of f of x is equal to 2, i.e. it exists, so it's continuous at -1. That's not a point, that's not a value of discontinuity. So continuous at x equals -1. We didn't get a discontinuity at -1, which good, bad, doesn't like, there's no morality to this problem, so it's okay. And notice that I didn't underline it because I don't want to get it confused with the actual points of discontinuity. Couple things just in terms of when you're writing this on on an example problem or on an exam or on a quiz, you don't have to write this. The limit as x approaches -1 of f of x. You can immediately skip to that. I'm just saying I'm taking the limit of a piecewise function, and on that piece it's equal to that. That's what I'm saying. I'm being very, very particular in my language. But once again, the rule of thumb for how much work to show is a person of the same intelligence in calculus should be able to look at your work and know what you did. So, Jaden, you look like you have a question.
Process.
For sure. I get that. I get that a lot with my courses too. So the next one, for x equals 4. F of 4. In that case, we're looking at the bottom function, the third part. And so we'll plug in 4. -4 quantity squared plus 26, excuse me. That'll be 16. Oh, sorry. What am I doing? Negative quantity 4 squared plus 26. That'll be positive 10. Okay. So the function exists. That's not enough, though. You need function to exist, limit to exist, and then to be equal in order to have continuity. So now we'll check the limits. The limit as x approaches 4 from the right of f of x would equal the limit as x approaches 4 from the right of that same function. So it's going to be the same calculation. I know it's tedious, but they are two separate things. Think of it as in English, writing a statement and then a clarifying statement or to add on to it. Because you're saying, like, first thing is you're saying the function exists. The next thing is you're saying that a limit exists. Yes.
4 is a dividing number.
Mm-hmm.
How do you determine which piecewise you use? The one that has the equals under it? Because we did that same thing for -1, since it was the dividing.
Yes. Excellent question. So it all has to depend upon the inequality. So if we're talking about x going to 4 from the right, that means that our x values are going to approach 4 from numbers that are slightly larger than 4. So looking at the function, those are the numbers that are slightly larger than 4. So we're using the bottom function. If we're approaching 4 from the left, we're talking about numbers like 3.9, 3.999, 3.999, and we're getting closer and closer to 4. But every single time we test a value, we're going to be less than 4. So we're going to be using the secondary one. So that would be of -x squared plus 26. And for the same reason, you'll get 10. And so, oh, it's looking good. It's looking good. But the limit as x approaches 4 from the left of f of x, that's the middle function. That's the limit as x approaches 4 from the left of 2, which is equal to 2. Not equal, which implies that the limit as x approaches 4 of f of x does not exist. And because the limit, oh, I'll let you write that down first. Because the limit does not exist, it fails continuity. You need the function to exist, limit to exist, and both be equal. Since the limit does not exist, we're all done. We don't need to do any more. We don't even need to check whether or not they're equal. The one of them doesn't exist. So discontinuous discont at x equals 4. And then I'll underline that, or let's use red to underline. or use the highlighter, yes.
So either one that is sufficient though to say it's discontinuous, one that it does not exist, and or two that it's not equal, right? Either one.
Yes.
is the same thing.
Yes. And that, like, that gets back to a point that I mentioned very, very briefly, is that technically speaking, like, if you look at grad textbooks, when they talk,
Vacuously satisfying? Is that what you
yes,
said?
yes, vacuously satisfied is what I want to imagine every mathematician saying that. And so the third condition basically guarantees the first two, but it's just for earlier in our mathematical career, it's better to see it that way as 3 steps. But later on, we skip that step. So we've checked the pieces, we've checked the dividing values, we're all done. And notice that this problem says find the x values where it's discontinuous. It doesn't say find the intervals of continuity, it says find the x values. So we don't need to write any intervals, we just say discontinuous at x equals, what was it? The first one was -3 and 4. Done deal. All right. Now we get to some fun questions, some super fun stuff. Love this problem. This problem's a lot of fun. So find a constant k such that the function below is continuous everywhere. Love these problems. Maybe a hint, hint, wink, wink. Not on a quiz, heavens no. But maybe on an exam, might happen. You never know. I love these problems. So, step 1. Let's make sure that the problem itself is actually well defined, because if there's a spot where these functions are discontinuous, that would be a problem. For y equals k e to the x plus 2 on x greater than or equal to 1. No discontinuities. But Phil, there's that k there. Remember, k is just going to be a number. We don't know what it is, but it's just a number. 5e to the x plus 2 is continuous everywhere because exponential functions are continuous everywhere. Because if you look at the domain of it, you can plug in whatever number you want into an exponential and you always get a number, whether it be -10 billion or +10 billion. You can plug in whatever number you want into an exponential and you always get a value. So there's no discontinuities there. For y equals 2x plus 1 on x less than 1, also no discontinuities. That step isn't required to check. You can just, like, because this is just asking to find what the k value will be, but it's not a bad idea to include it. Step 2. For x equals 1, that is our dividing value. F of 1 is equal to ke plus 2. It exists. We don't know what the number is. K times E is some number. We don't know what it is, but it's still just a number, so it exists. That is good news. So we can't solve for K here. So there must be some way to figure it out. Not guessing and checking, that's not going to work. That's not going to work. You can't just say, maybe try 3, maybe try -3. But this will show you. So in order, like, you can, like, based on everything that we've learned, we can figure this problem out. There's nothing stopping us. We need the function to exist there. We also need the limit to exist. And since 1 is a dividing value, we'll check the left and the right-hand sides. So the limit as x approaches 1 from the right of f of x, that would be the limit as x approaches 1 from the right of the top function, k e to the x plus 2. And remember, for a limit, any alternate variable that's separate from the variable for the limit. So this is an x limit because it's as x approaches 1 from the right. The k is just a constant, so you don't need to worry about it. You don't need to plug anything in. So this becomes ke plus 2. Yes, it's the same calculation, I know, but once again, it's a different context. One of them is calculating a function value, one of them is calculating a limit. And so we need this to be equal. So we'll check the left-hand side. One from the left of f of x. That would equal the limit as x approaches 1 from the left of 2x plus 1. And that's a polynomial with no dividing errors, no square root errors, no nothing like that. It's just a nice, neat line with slope 2 and y-intercept 1. So we can just plug in the value and call it good. That'll be 2 times 1 plus 1, that's 3. That is not the same number yet. We need these to be equal. Need equal in order for the limit as x approaches 1 of f of x to exist. And that allows us to solve our equation. That allows us to find out what k should be. In order for these things, in order for this to be a true, like to be continuous there, we need those two things to be equal. So we solve that equation. K times e plus 2 is equal to 3. And remember, we're solving for k, and e is just a number. It's 2.71-ish. Or wait, 2.74-ish, right? E to the first power is 2.71-ish. Sorry.
-1/e.
Yes, so we'll subtract 2, we get ke is equal to 1, which gives us k is equal to 1/e. Or e to the -1, however you want to write it. I'd prefer 1/e, but we have found a way to make sure. Now we could go through the whole motion now of like saying, okay, plug in that value and see if f of 1 exists and that its limit exists. But by our work, we've already verified that. So that is the value of k that will work. And here's a cool thing you can do, by the way. If you know how to work with Desmos, you can plug in the function y equals k e to the x plus 2 and have a slider. And then also plug in the function y equals 2x plus 1 and mess around with k, and you'll see the function starts to change a little bit. And depending on what k is, it'll actually end up connecting to the graph. It's very, very cool. So definitely try that. Like what'll end up happening is so 2x plus 1, that looks like 4 values less than 1. So it looks like this. And then depending on what k is, it'll either look like that should be at 0. It will be, oh wait, no, at 1. And the curve would be like, it'll start to look like this, and it'll start shifting, like make it look like this. And then eventually, once you get k equals 1/e, it'll connect and make it continuous. Very fun project to do. Any questions on that? Yes.
So working in reverse, you can just figure, you notice that there's nothing not allowed in the domain of either piece. And you just find the limit of the 2x plus 1 because it's easier, and then just set the more kind of abstract one equal to 3.
Because we need the limits to the left and the right hand limits to be equal to each other in order for the full limit to exist. And that's the condition of continuity that we need to satisfy. We already found out that the function exists there. I'm going to write, by the way, that this is optional work. It was not necessary for finding the answer, but it's a good thing to check. All right. Now a super fun problem. Find the constants a and b, not just k, but find the constants a and b so the function is continuous everywhere. Step 1, we're going to skip it. If you look at all 3 of these functions, you'll see that all 3 of these functions are defined everywhere. Cosine exists everywhere. X is defined everywhere. 7 and 5 defined everywhere. Skip step 1. Because all pieces are fine. The way your significant other would say, it's fine. Not that fine, but it's totally fine.
Remind me why cosine isn't between -1 and 1. What is that domain again? Cosine?
That's its range. Cosine is a range of -1 to 1. So it's y values. The values it spits out are between -1. The cosine of pi x is it's a shortened graph. It's got a higher frequency. But it still is just a nice continuous curve.
What would make one of these pieces not fine?
If it said something like cosine of x over x, that would cause issues. But then this problem would be a bad problem because it would be saying try to find the places that make sure this thing is continuous everywhere, which it can't be because that's a limiting factor. So step 2. The limits, well, we got two dividing values for x equals 1. I'm going to skip plugging it in because that's kind of just taken care of by it. But, well, actually, we should still do it. F of 1 is equal to a cosine of pi plus 2b times 1. That's what's cosine of pi, everybody? Resounding -1. Cosine of pi is -1. You all know our trig. Good. I'm glad. So that's -a plus b, 2b, excuse me. It exists. We don't know what it is yet because we don't know what a and b are, but a and b are just numbers. So maybe a is 1 and b is 5. So then -1 plus 2 times 5 is +9. It exists. We don't know what the number is yet, but we do know that that is a finite number. We didn't divide by 0. We didn't take the square root of a negative number or anything like that. Because a and b are just numbers, it exists. So the limit as x approaches 1 from the right of f of x would equal the limit as x approaches 1 from the right of the middle function, a cosine of pi x plus 2bx. And I know that looks scary, but a and b are constants. They do not depend upon x. So you can ignore them and just plug in 1. We're not dividing by 0. We're not taking square roots of negative numbers or anything like that. So we're fine. And so this will be a cosine of pi plus 2b times 1. That's a plus 2b. That is the limit as x approaches 1 from the right. And you'll see then by a similar argument, the limit as x approaches 1 from the left of f of x, that's going to be using the top function because for values slightly less than 1, talking about less than 1, so you're going to be the top function. That'll be the limit as x approaches 1 from the left of 7, which is 7. We need these equal. In order for this thing to exist, in order for that full limit to exist, we need it. So we need a plus 2b to equal 7. Uh-oh. This isn't like the previous one. We can't solve for a and b at the same time. Phil gave us an unsolvable problem. There's like, if you've seen that picture of the otter trying to put the caps in, it says, you gave me unstackable cups. Does anyone know what I'm talking about? No, it's probably a stupid thing. But just, you gave me a bad problem, Phil. No, I didn't. That must mean there must be a second equation out there. Let's use the other dividing value. Oh, we don't have enough room. Oh no, let's just erase this. Or I got it. So everyone just do this with your notes, just make it smaller. I'm sure you guys can all do that, right?
Having infinite extending chocolate things.
Yes, indeed. I'm sorry, guys. I thought, actually, wait. The next problem, you can keep working down there. We're going to omit that problem. The intermediate value theorem is not important. It's super important, but not for us. I'm not going to ask any questions about the intermediate value theorem. Yes.
The a plus 2b, isn't it negative a plus 2b?
Negative a plus 2b. Yes, negative a plus 2b. So negative a plus 2b. All right. Thank you for catching that. Thank you. We had written it up here. Okay. For x equals, what was the other dividing value? 2. For x equals 2, f of 2 is going to be equal to 5, so it exists. And then we'll check the limit as x approaches 2 from the right. And just to save on time, and saying what you can do on your notes, limit as x approaches 2, that will be the bottom function. So you can just write the limit as x approaches 2 from the right of 5, which will equal 5. And the limit as x approaches 2 from the left would be of ax plus, or a cosine pi x plus 2bx. And just like before, a and b are just numbers that don't depend upon x, so you can just plug in 2. You get a of cosine of 2 pi, a times cosine of 2 pi, excuse me, plus 2b times 2, and cosine of 2 pi is 1. There we go. Good. Resounding 1 from everybody. We all know our trig. So that's a plus 4b. And we need these equal. So we have a plus 4b is equal to 5. Oh no, I got another one that I can't solve because it's got 2 variables. Yeah, if you're just looking at one equation, but we've got a system of equations. We've got negative a plus 2b is equal to 7, and a plus 4b is equal to 5. That's a system of equations. Bet you didn't think you were gonna have to do that again, did you? Thought you thought you were done? No. Systems of equations will come back again and again and again and again and again. In 182, you'll have to solve for different variables with a system of equation in what we call partial fraction decomposition. If you decide to take math 283, when you're trying to find the critical values of multivariable functions, you'll have to solve systems of equations again. So these things stick around. Anyways, the good news here is I designed this one perfectly so that you can use the elimination method and just add down. But however you like to solve systems of equations, if you like to use the substitution method, go ahead. I just like the elimination method, so I'm just going to add these two together. And that'll cancel the A's, and I get 6b is equal to 12, which tells me that b is equal to 2. And then I can use either equation to solve for a. I'm going to use the first one. Actually, let me use the second one, because then I don't have to deal with a negative a. So a plus 4 times 2 is equal to 5. That gives me a is equal to negative 3. And that is my answer. Wasn't that fun? Come on. It's a fun problem. Super fun. Making sure you understand continuity using one-side limits and solving equations and systems of equations. Are you kidding me? That's a fun Friday night for everybody, right? I'm glad. Okay. So just omit this one, by the way. Omit. While the intermediate value theorem is very, very important, it's important for math majors, not for anybody else. You're never going to be asked about the intermediate value theorem in your daily life. I can get, like my brother, once again, my brother's an engineer, and he has never used the intermediate value theorem since graduating. So I'm going to take that as a sign that we don't need to do this. It's really just useful for proofs. Okay, let's see the time. This will be a perfect time to take a small break. I'll pass back the quizzes. Let's come back together at 11. No, let's come back together at 12 o'clock. People watching the review, people watching this, go do some guided meditation, some yoga. All right. So I realized when we got to class that I had forgotten to put this on the course homepage. I will update that as soon as I can. Like right after class, I'll be posting this so you can print it off. I'm so sorry about that. Won't happen again. But so we'll just work through this one. If you guys need scratch paper, I've got some scratch paper if you need to take notes. So sorry about that. But we're gonna be starting the next unit, and you might be thinking, Phil, if you've looked at the exam, as a reminder, so exam next week. Exam is next week, and it's going to cover all of Unit 1 and 2.1. So it's going to include 2.1, and you'll see why once we get to it. So
You said only 2.1?
Yeah, only two, like from chapter 2, from unit 2, only 2.1. Specifically, just the definition of the derivative, honestly. But we'll talk about that in a second. So the definition of the derivative. Have I talked about Leibniz and Newton in this class yet? I don't think so. Okay, so from pre-calculus, you might have remembered the average rate of change, capital F of B minus capital F of A over B minus A, right? So some people would write M, font. Some people will write M sub AVG, but the more scientific, like the more mathy way to write it would be M sub SEC for the secant line. M sub SEC was equal to F of B minus F of A over B minus A. It's calculating the slope of the line connecting 2 points. So if I had like, this is a secant line right there, through those 2 points. That's a secant line. Don't draw that yet. But well, I mean, you can't. No, I'm sorry. I'm so sorry. I feel terrible. But that's what we call a secant line. And then the question then becomes, how do we draw a line that is tangent to the curve, at least locally, right? If I draw this tangent line right here, it does cross the graph at another point, but locally, right here, if I just examine that spot and draw it better, it's only going to touch the curve at that one specific point. That is a tangent line. And so the question then becomes, how do I get a tangent line? How do I find out what the slope of that line would be? Like, I can't, like, yeah, you could try and guesstimate it, but if you're not given any information about the scaling, how do you know what the correct line should be? How do we know that that's the slope? And so mathematicians said, well, what if we take the secant line and we just make A and B get closer and closer together? So as an example, here's A and here's B. And this is that first secant line. And that's pretty close to being tangent, but not great. And then maybe we just make A and B a little bit closer. And then we see it's even more accurate. And then finally, what if A and B are synonymous points? One might say, so what would we be doing there, guys? What would we be doing if we were making A and B get infinitely closer together? What would we be doing? We'd be finding a limit. So that's the reason why we study limits in the first place, because derivatives and integrals, which we'll see in a little bit, well, not in a little bit, in quite a while, limits are what is used to define a derivative. A derivative, or sorry, a tangent line, that is. A tangent line is found by looking, just let me do that. There we go, good enough. A tangent line, the slope of it is found by taking a limit of the secant line, the slope of the secant line, that is. So this brings us to the concept of the derivative, which I want to make sure which one do I put first for you guys. Yeah. Okay. So let f be a function, then the derivative of f, which is denoted by f and then an apostrophe. And we say f prime. Back when I was a young math student, just starting my major, I wanted to be silly and I wanted to make my own function that would involve derivatives, and I wanted to call it the Optimus function. So then you'd have Optimus prime. Then later on, I learned about, in Calc 3, you'll learn about del, which is has to do with multivariable functions. You call that del. And I wanted to make a taco function, so that I have del taco. But sadly, couldn't figure out anything that would work that way. So the derivative is defined as f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. That is the version that we will use almost exclusively. Or f prime of x is equal to the limit as t approaches x of f of t minus f of x divided by t minus x. I know t is just a variable. I could have just as easily used a whatever, and a is as it approaches x. So these are synonymous. These are the exact same thing. The first option is the one that's better for calculations. When you're trying to find the definition of the derivative, when you're trying to find a derivative formula, that's the function you use. When it comes to proving things in mathematics, the secondary version of it is far more useful. Almost every proof that involves like something about derivatives, if it's going to prove something with derivatives, it almost always uses this format. But this format's far more useful for finding things. And you might be thinking, Phil, it doesn't look the same. It does, it's just already simplified, because just instead of t, make it an x plus h minus x, and then the x's cancel, and that's why it's the same thing. But either way, we're mostly going to be using the first version, but the second version is still useful. So being comfortable with both is useful, but more so the first version. Anyways, I'm getting sidetracked.
So the minus x on bottom is that same thing you just said with the x plus h minus x, so that's why it's present in the second synonymous function?
Yes. Yeah. Okay. So if you're trying to find a specific value, like a specific, like, so these are the slopes of the tangent lines. But that's at a various point x. If you want to find the slope of the tangent line at a specific value, if you want to find the derivative at a specific value, let's say a, then all you need to do is replace the x's with a's. So, like i.e., f prime of a would be the limit as h approaches 0 of f of a plus h minus f of a divided by h, or f prime of a is equal to the limit as t approaches a of f of t minus f of a all over t minus a. Yes.
F prime could be most already factored.
F prime is just the name of the derivative. So f prime of a means the derivative at a. In terms of mathematical jargon, just because it hits the ear wrong and it makes me mad, we are taking the derivative. We are performing differentiation. We are not deriving the function. Deriving would mean creating, not taking a derivative. So just please don't say derive the function. It just hits the ear wrong. You will say that you are differentiating the function. You are taking the derivative. Okay? The other thing is that this notation is what we actually call Newtonian notation of the derivative. There are many other ways to describe like that we've denoted derivatives. Of most important note would be dy, so f prime of x, dy dx, df dx, so df over dx or dy over dx. And then if you look at some really old textbooks, they might say df like that, etc. There are many different ways to write it, and the context is useful. So this is Newton notation, and this is Leibniz notation. So it's a fun little history lesson. Just a fun little history lesson. I'm pretty sure we all know Isaac Newton. He's a pretty famous dude. Yeah. He's very smart, very smart. But there was another mathematician at the same time, Gottfried Leibniz. And they were both discovering calculus independently. Newton thought of it more as a function, but Leibniz thought of it as a ratio. So have you guys seen the terminology delta x like that? Meaning a change in x, and delta y meaning a change in y. What is a slope? A slope is a change in y over a change in x. And what we're doing with the tangent line is we're making that change in y and that change in x infinitely small. So Leibniz created his notation and he called these things infinitesimals. So an infinitesimally small change in y over an infinitesimally small change in x. And back in the day, so it's very hard to communicate with the other people. Newton was in England. Leibniz was in, I believe, Germany. I don't know my Europe geography very, very well, but I believe it's in Germany. But they were finding it separately. When his papers got published, Newton's papers got published, Leibniz saw them and said, hey, I'm working on something similar. Do you want to work together? And Newton said no. So it's a big deal. It's actually very, very interesting. So the rest of England followed Newton, their golden boy. And the rest of Europe followed Leibniz. Because screw England. No, I'm kidding. But they followed Leibniz's notation. They followed calculus through his lens. And it allowed them to figure out a lot more mathematics. The rest of Europe actually advanced in mathematics far faster than England because they were stuck with Newton's notation, which is very, very good and well organized. But Leibniz has created an intuition about this fact of an infinitely small change in x that's dividing into an infinitely small change in y. Key thing about that, dy dx is not actually a fraction. It's not a fraction. It's its own variable. So it's got 4 letters in it, but it's a variable. Like it's a defining a function. It's not a fraction. However, on occasion, you can think of it like a fraction. If you start to take math 283 and beyond, you'll start to realize why we can't necessarily call dy dx a fraction. But back in the day, it allowed mathematicians to say, okay, so if it was a fraction, I could do this. And then they discovered many different things. They're like, okay, so I can manipulate this fraction and it ends up being really, really useful. They discovered the chain rule far before Newton's world. They discovered the inverse function theorem far before England did, and a lot of other mathematics. You see a lot of German names, Polish names, all other parts of Europe. You see way more of their names and theorems than you do English people. And it's because they followed Leibniz's notation. Both notations are very, very important, and we will be using them in different contexts. So it's important to get comfortable with both. I will be interchanging the both of them because in certain circumstances, it's better to use Leibniz's notation. In certain circumstances, it's better to use Newton's. So make sure you're comfortable with both of them, okay? Any questions on that? So yeah, oh yes, go ahead.
Even though it's better to use one in certain cases and the other, it would still derive to the same answer?
Yes, they will still give you the exact same answer. The funny thing, sorry, one last thing, is because of the way Leibniz defined it, he actually had to create an entirely new form of mathematics. The way we teach it nowadays is with the functional notation, with Newton's notation, because it is easier to visualize and to work with. But there are old textbooks that follow Leibniz's calculus to a T, and it just requires a little bit of extra work to convert between the two of them because he created an entirely new type of quantity called an infinitesimal. And can you actually make division by infinitesimals? Can you divide by 0? No, but can you divide by an infinitesimal? Hypothetically, yes. And so there's all this. There are textbooks that try to convert Leibniz's notation into Newton's, and you'll see that it works out, but it just takes a lot of extra stuff that we don't need to worry about. Anyways, I'm getting sidetracked because I just love that history lesson, the fact that England got left behind because they followed their golden boy. So key fact number 1 about this. By the way, does anybody know what this looks like? Does anybody remember this from 126? The difference quotient, yes.
Thing. So both of those are an example of the Newtonian notation?
So, excellent question, excellent question. Back in that day, it didn't have this formula like this formula. Newton's notation was F prime, but the formal definition of a limit didn't come for much later. That required people like Augustin Louisville Cauchy, and I think what's his name, Weierstrass, and a couple other people. They formalized the definition of the limit. Up until that point, it was really, really informal what they meant. So like they kind of read it out saying this is like an infinitely small change in X and an infinitely small change in Y. They didn't write limit notation. But now with these new math, like with Cauchy and a few other mathematicians, they formalized it and then said, okay, then calculus should be represented this way. So derivatives are represented that way now. Is that okay?
Yeah, so not necessarily Newtonian, the F prime
Yeah.
equals those two.
You could just as easily write dy. You could just as easily write dy dx equals.
Yeah, because I almost would have made more sense, just even though it's not a fraction, but it looks like more like a ratio.
Exactly. No, exactly right. It looks more like a ratio. It is an infinitely small change in X between the point A plus H and A. They're very, very close together. And then an infinitely small change in X. That's a Y. Sorry, I keep forgetting that I need to write. This is a change in Y. This is a change in X. So it literally is a ratio. And when you can think of it like that, you can create all different types of fun mathematics. Specifically, the most common one that is like, once you see it as a fraction, the inverse function theorem is like that. The proof of it is monstrous, which we'll talk about, but the actual theory of it, like the rest of Europe was like, oh, if it could do that, then it would work. I'm getting ahead of myself. I promise it'll start to make more sense when we get there. Anyways, so we're dealing with a difference quotient. And there was a reason why we made you study that in 126. And there was a reason why we had you simplify it. So key fact number one is when calculating the derivative, when calculating f prime of x by the definition, you're not done until you cancel the h in the denominator. You're not done simplifying until you've canceled that h in the denominator. So if you still have an h, you're not done. You have to keep working through it.
Because that would be essentially still the 2 points separate, and as soon as you eliminate the H, it's created that 1 point in the middle.
Essentially, yeah, you've found that spot. But in particular, if you don't get rid of the h, then you're going to be dividing by 0 every single time, and that's a problem. So find f prime of x for the function f of x equals x squared minus 3x plus 2. So when you're memorizing this thing, it's always good it's free practice to just write the formula over and over again. Whenever you do a new problem, rewrite the formula. F prime of x, by definition, is the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Now, as you get better and better and better with your algebra and your comfortability with this formula, you can plug this in at the same time. I don't recommend that when you start off. I like to calculate these things on the side. I like to calculate f of x plus h on the side and f of x on the side. Well, I mean, f of x was already done, but f of x plus h. So don't write this down because this is incorrect. John Doe student, silly John Doe, it's always wrong. He writes this. Why is he wrong? That's not correct. That is not putting in x plus h into the function. That is adding h. This is f of x plus h. Do we see the difference? Very, very important. I say it's very important because if you do this, what I didn't read, you will get the problem wrong 100% of the time. Every single time you will get it wrong and you will get frustrated. F of x plus h is taking the quantity x plus h and plugging it into every instance of x. You're plugging in x plus h into the function. So f of x plus h, this is the correct way. f of the quantity x plus h is the quantity x plus h squared minus 3 times the quantity x plus h plus 2. And since we are going to need to do some simplification, let's just go ahead and FOIL it. And John Doe student does another thing. What did John Doe student do wrong? He broke my heart. You got to FOIL. X plus h squared is not x squared plus h squared. That's what we call the freshman's dream. True story. It actually has a name. It's called the freshman's dream. It's not true. You got to FOIL. You got to FOIL. So this is actually x squared plus 2xh plus h squared minus 3x minus 3h plus 2. Once again, I'm sorry that we don't have the notes in front of us. I'm sorry about that. I will post them right after class. So now that we have that ready, we already know what f of x is. It's just given. Now we know what f of x plus h is, and h is just h. So we can plug everything in. So this is the limit as h approaches 0. And yes, we still follow all limit rules. Still follow all limit rules. We don't drop the limit until we can take it. And we can manipulate the limits as much as we want. We can factor, cancel, we can multiply by things. All that stuff is still valid. So limit as h approaches 0 of x squared plus 2xh plus h squared minus 3x minus 3h plus 2 minus one last time. So I'll let you write that down. And one last time, John Doe is going to be wrong. Why is John Doe wrong? Didn't put parentheses. You will, if you forget to distribute, you will get the problem wrong 100% of the time. And that's a true statement. 100% of the time, if you do not distribute, you will get the wrong answer. And you might be thinking, you might be saying, well, Phil, I know what I meant, and I'm totally willing to skip that step. It's 2 extra lines that take way too long to write. It's not worth it to me. And yes, I believe you. I believe that you know what you're doing, but I don't trust your environment. Maybe while you're doing this, some guy is eating a head of cabbage during the exam, or someone sneezes, or like my chemistry exam, gets up in the middle of it and says, I can't do this, and runs out. And that would completely distract you. That would completely distract you. And then you forget to distribute. Everything goes to crap. You fail the exam, which means you fail life, and then you die. So that's what I don't want to happen. Please put the parentheses. It's 2 extra lines. I know I joke about carpal tunnel, but this is worth it. This is worth the risk of increasing your chance of carpal tunnel. Put the parentheses. X squared minus 3x plus 2, all divided by h. And then that minus sign needs to get distributed in. One last thing is that if you feel comfortable skipping algebra, please do so. The more algebra that you can skip, the less chances you can make mistakes, right? Less chances your h's might look like a 1 in weird contexts. But anyways, while we're still doing this for the first time, I'm going to show all the algebra. So this will be limit as h approaches 0 of now x squared plus 2xh plus h squared minus 3x minus 3h plus 2 minus x squared plus 3x minus 2, since we distributed that minus sign, all divided by h. Now, I guarantee you, if you try and plug in h equals 0 right now, you'll get 0 over 0, which is telling you that you need to do something. Something needs to be happening. And the thing that's going to happen is simplification. We're looking at this. Oh, isn't that nice? The x squareds cancel. Oh, those 3x's cancel too. That's nice. I know those 2's cancel. Huh. It's almost like that was by design. It's almost like that will always happen. It will. Well, there's always a way to cancel it. There's always a way to cancel it. And so what we end up with then, if all those things cancel, and leave a little bit of space next to this equal sign, so this will be the limit as h approaches 0 of 2xh plus h squared minus 3h, all divided by h. And there's a common factor of h throughout the entire thing. So the numerator is h times 2x plus h minus 3. And the h's cancel, and that was the thing that was causing an issue. Now that we've gotten rid of that h in the denominator, we can take the limit, so we're going to drop the limit sign and plug in h equals 0. So this will be equal to 2x plus 0 minus 3, or preferably f prime of x is equal to 2x minus 3. We just calculated our first ever derivative.
Plugging the limit to simplify difference quotient to get the derivative.
And so since this was an arbitrary x value that we didn't decide what x was, this is the function that's the derivative. There's a key important connection between the derivative and the derivative function and the slope of the tangent line, which we'll get to in just a moment, but that's the derivative. One last just algebra mishap that I want to make sure we nip in the bud is this. Once again, John Doe student, man, he's really screwing this one up. Do not make this mistake. That's not valid. You can cancel factors. You can't cancel terms. Like, sure, you could divide it into each one if you wanted to, and that's fine. But the point is, you can't cancel terms. You have to cancel factors. So that's why I had to factor it up here first. So don't be a silly John Doe student. Don't make that mistake. All right. Next problem. We're going to find dg dt, i.e. g prime. dg dt, g prime are synonymous. So, and it's of a function of variable t, but the variable doesn't matter. The reason why I want you to, like, I usually use x's and t's because if you're planning on taking physics, a lot of things you study in physics are things of time. So you want to be comfortable with the t variable as well. So g prime of t, or dg dt, is equal to the limit as h approaches 0 of g of t plus h minus g of t all divided by h. And if you feel comfortable, like this one wouldn't be too terrible to simplify as you're going through it. But I'm still going to calculate it on the side. There's nothing wrong with doing it as you go along. And there's nothing wrong with doing it on the side. It's just your prerogative. I just like to work in steps. So g of t plus h would equal 1 over t plus h plus 3, or preferably 1 over t plus h plus 3. I know that was an unnecessary step, but it's, once again, it's for your notes to say I plugged in t plus h in for t. I replaced every instance of t in my formula with a t plus h. Or I replaced every instance of x in my formula with an x plus h. All right, so this is equal to the limit as h approaches 0 of 1 over t plus h plus 3. Leave a little bit of space, then write the minus sign, and then 1 over t plus 3. That's what g of t is, all divided by h. If you try and plug in h equals 0, you get 0 over 0, which is a big no-no, but that means there's something we can do. What can we do? Factoring isn't good, like we don't have any factors to work with. We got fractions. Common denominators. There we go. If you're not certain, just try something. Worst thing that happens is you have to erase it. So I'm going to multiply by a common denominator. That's t plus 3 over t plus 3. And then I'll multiply this one by t plus h plus 3 over t plus h plus 3. Granted, if you want to use the other method that I talked about when it comes to complex fractions, if you looked at that video from the algebra section, you can definitely do that method too. It'll work just as fine. But this is the convention. So that will become the limit as h approaches 0 of t plus 3 minus parentheses t plus h plus 3, all divided by t plus 3 times t plus h plus 3 and then all divided by a big bar of h. Once again, feel free to skip algebra wherever you feel comfortable. I'm not testing you on your algebra skills. I mean, kind of, because algebra is like 90% of this course, but I don't need you to show all the algebra here. Yes.
Speaking of algebra, on a fraction, the negative should only distribute to the numerator.
Yes. Yes. So that will be the limit as h approaches 0. When you distribute this minus sign, wasn't that nice? The t's cancel. And also the 3's cancel. That must be nice. That must be happening by design. It is. So that'll be negative h divided by h times t plus 3 times t plus h plus 3. Make sure you understand where I got that from. If you don't, please let me know. Please take a second to think about it. And then if you still can't figure out, please feel free to ask.
It's 1/h, right?
Yep, it's because you're dividing that whole big fraction by h. That's the same thing as dividing by h over 1, which means you're multiplying by 1/h, because you divide by fraction, you multiply, and that's why there's that h in the denominator now. And luckily for us, that means that it cancels. Yay! We still have a -1 then. And so, if you want to, you can rewrite it, or you can just plug it in now. Now that we've canceled the h, we can plug in h equals 0 with no problems. That was the problem. When the h was there, we'd be dividing by 0. Now that it's gone, it's done. And so this is going to be -1 over t plus 3. There's no h's to plug in there. And then t plus 0 plus 3, or preferably dg dt is equal to -1 over t plus 3 squared. So it's a rite of passage in mathematics. It's a rite of passage in every calculus course. I don't care where you're from, whether we're talking about in Maine or over here. Almost every first calculus exam has a definition of the derivative problem. Hint, hint, wink, wink. Maybe we should practice this before the exam, right? Maybe this will show up. I can neither confirm nor deny the existence of it as your teacher, but if I was a betting man, I'd say this would be a good thing to study. Hopefully that makes it clear enough for everybody. We all good? All good, understand that? Okay, cool. All right, another one. This one, just in the interest of time, I'm going to tell you what the answer is. I want you guys to practice this one. This one's a good one to practice. Highly recommend. The answer will be that dy dx is equal to 3 over 2 square root of 3x minus 4. And that'll be the answer. Yeah. But please check that on your own time. The key, conjugates. Try this one. Please do so as an extra practice. Just one of the biggest things I can help recommend to you as math students on how to be more successful is after every class, try and do at least like 1 or 2 problems later in the day so that it refreshes it in your mind. It will help you immensely. I promise you, if you take like 10 minutes, 15, 30 minutes to do a couple practice problems at the end of the day, you will better retain the information. So that's the key. On Wednesday, I'll make sure I have the written work here so you can check it with your answer. But for now, I want to move on to key fact number 2. So as we saw in those last 3 examples, the derivative is a function. The derivative is a function, that's true. But you can also think of it visually. So the derivative, let's say when evaluated at a point or at a value x equals a, f prime of a represents the slope of the line tangent to f at x equals a. As we saw with that graph, when you plug in a specific value, your function produces a number, right? When you plug in a value into a function, it produces a number. And when it comes to the derivative, it will represent the slope of that tangent line, as we saw with that picture. When I calculate it at a, it will give me the slope of this line. Because at the end of the day, it is a secant line where we make it's a limit of a secant line. And like limit of the average rate of change, excuse me. And the average rate of change is a slope. The average rate of change is the slope of that line that connects the 2 points, and the limiting process makes it the tangent line. So the tangent line, the slope of the tangent. Let me restart that. I'm not happy with how I said that. So the derivative, the definition of the derivative is just taking an average rate of change and making it limited, limiting that process, making the two numbers come closer and closer together. And once it comes closer and closer together, those points actually form a tangent line. So that's what it is. This is the slope of the secant line. This is the slope of the tangent line. So when you plug in a specific value into a derivative, you're getting the slope of the tangent line at that point. It is a value, but it's also interpreted that way at the same time. So for f of x equals 3x squared plus 1, find f prime of 1 by the definition, then find the equation of the line tangent to the graph at x equals 1. Okay. That time we're good. Good. How much do we have left? That page. Okay, that page. That page. Okay, so we're quote unquote a little behind schedule, but not really. All right, so f prime of 1. This is where I would recommend, honestly, I would recommend using the secondary version of the function, the definition of the derivative. It would be easier that way. However, just because we usually like to use the other one, I'm going to do that. This will be the limit as h approaches 0 of f of 1 plus h minus f of 1 divided by h. And off on the side, f of 1 plus h is 3 times the quantity 1 plus h squared plus 1, which if you plug that, if you finish that, that'll be 3 plus 2h, so 6h plus 3h squared plus 1. So that's really 3h squared plus 6h plus 4. And then f of 1 is 3 times 1 squared plus 1, which is 4. I encourage you, by the way, to do it the other way, using the other definition of the derivative, when you've got some spare time, and you'll get the exact same number. You should. If you don't, then you made an error. But anyway, now that we got f of 1 plus h and f of 1, plug them into the formula, and we'll be golden. This will be the limit as h approaches 0 of 3h squared plus 6h plus 4 minus 4. And yes, I didn't put parentheses, but it's only because I have one term. Otherwise, I would have put parentheses just to avoid possible issues. Divided by h. Isn't that nice? The 4's cancel. And we've got the limit as h approaches 0 of 3h squared plus 6h divided by h. You're not done with a derivative until you've canceled that h, but we can because there's a common factor in the numerator. Factor that out. This is h times 3h plus 6. Really bad handwriting. Let's make that better. The h's then cancel, and we can plug it in. You get 3 times 0 plus 6. Once again, you can always, in my class, if you want to skip some arithmetic, skip some algebra, do so. I'm just writing that so we're clear on what's happening. We're plugging in h equals 0 so that we see it in our notes. This is just for our notes. If you want to skip steps, be my guest. So, oh yes, Louis.
So that 6 is the slope of the tangent line of the value 1.
Exactly right, exactly right. So hopefully everyone heard what Louis said. If not, this, let's use purple. This is m sub tan, i.e. the slope of the line tangent to f of x equals 3x squared plus 1 at x equals 1. That's the slope of the tangent line. Like if you were to draw a line with a slope of 6, it will be parallel to the tangent line. But we've only got the slope. And does everyone remember, when you're trying to find the equation of a line, you either need 2 points or you need a point and the slope. So we have the slope, but we don't have a point. Oh no. What do we do? Have the slope, but need a point. Well, what do we do? One is the x value. So we're talking about a line tangent to f, not to f prime, but a line tangent to f at x equals 1. So we need a point on f. Since x equals 1, f of 1 is 3 times 1 squared minus 4 plus 1 is 4. That implies that the point 1 comma 4 is our point. So our point is 1 comma 4. Sometimes they give you the x value, they give you the point already. Other times they'll say at x equals 1, and this the understanding is that I'm giving you the x value, you need to find the y value, and that is a point on the graph of the function f, not f prime. A very, very classic mistake students will make is they'll plug in 1 into the derivative to find the point. That's not how it works. That's a point on the derivative, not a point on the function. This is some weird stuff, by the way. And so this is another reason why Leibniz's notation is way better, because if you're looking at your notes, an f prime can look like a smudged f. That's the problem. All right. Who remembers point slope form of a line? Yes, y minus y sub 1 is equal to m. I will never ask you to write your line in a certain formula, but I will always tell you that point slope form is way better. Point slope form is just a beefed up version. It's a like what you could say, jacked, right? When you're strong. It's a jacked up version of the slope intercept because you can always go from point slope to slope intercept. So this will be y minus 4 is equal to m, which is 6 times x minus 1. That is the way I'd prefer it. Or you can simplify it to get in the slope intercept form. Y equals 6x minus 6 plus 4, or y equals 6x minus 2. Either way is fine, but I'd always, so I'm gonna go off on a little bit of a tirade. No, in fact, I'm gonna go off on a tangent. I'll be here all week, okay, guys. Thank you very much. I think point slope form is far superior for a number of reasons. This format tells me where the point is on the graph, and it tells me the slope. This one doesn't. This one doesn't tell me where the line touches the curve. This doesn't tell me where the tangent line touches the curve. This one does. It tells me more information. The rule that I will tell you, if you need to use the tangent line, simplify it. In fact, that is a good rule for this class. I don't care about simplification unless it needs to be used for something. If you're going to use something in this class, simplify it. So for example, if I asked you to find the x-intercepts of the tangent line, the x-intercept of the tangent line, use the simplified form, use the slope intercept. If you're being asked to find the derivative of at a certain value, use the simplified form. That's the general rule that we'll follow in this class. If we need it for something else, simplify it. Cool? That is the rule of thumb that you should always follow in mathematics. If you need to set, like, if you need to use it for something, use the simplest form. If you don't need to, don't spend the time doing it. Don't worry about it. That is to say, just once again, that is the better format. You can fight me if you want, but you'd be wrong. Slope intercept form is the baby form.
So you, if we're answering the tangent lines formula, use point slope.
Yes. Basically, whenever you're trying to find a line, use point slope in this course. I will never mark you down though. If you want to write your line in slope intercept form, if you want to solve for b, like use the y equals mx plus b, solve for b, all that stuff. If you want to do that, I will still give you full credit. I never ask for a specific format of a line. So anyways, this example here. The derivative of y equals x cubed minus 2x plus 5 is y prime equals 3x squared minus 2. You can use this without proof. When I say that, I mean that I don't need you to find the derivative. I don't need, like, I've already given it to you. Y prime is the derivative. Determine the equation of the line tangent to the curve at 2, 9. So point is already given. Smiley face. We just need the slope, which comes from the derivative. Now they told us what the point was. That means our x value is 2. So m sub tan will equal y prime at 2. So that'll be 3 times 2 squared minus 2. That's 3 times 4, 12. That's 10. So we have everything we need. Y minus 9 is equal to m, 10. Minus x minus 2. That's the better format. Or if you want to be a chump, you can write it as, or I guess, 10x minus 20 plus 9. So y equals 10x minus 11. If you really want to be a loser. I have a beef with slope intercept form. I just like it's points just so much better. I don't get it. It looks more complicated, but so much better. Okay. Got 2 minutes. We cannot solve this problem. Ponder this over the next couple of days, the next day or two. So we have a quiz. The quiz will cover the last part of 1.4. So limits at infinity. It's like limit as x approaches positive infinity or negative infinity. It'll cover that. It'll cover 1.5 and we just learned 2.1. Let's skip 2.1. I'm going to edit the front page. It's just 1.4 and 1.5. Let's do that. Okay. I'll be posting an exam review later today. With our 1 minute. So I post exam reviews, and on the exam review, it has an answer key. And then I will also post a solution key. Answer key is just the answers. A solution key is how to do the problems. If you are studying for an exam, I highly, highly, highly recommend, and it's not even a recommendation, attempt the problems first. Do not look at the solution guide unless you are completely lost. You will put yourself in a situation where you won't want, like I learned from my mistake. When I took Calculus 1 my first semester, I looked at the exam solution guide. I was like, oh, that makes sense. It's good. But looking at something and understanding it is different than creating it yourself. So do the problems yourself. If you get the right answer, awesome, you did it great. If you didn't, try again. And if you don't get it right the second time, then look at the solutions and then try and recreate it yourself without looking at it. You will thank yourself when it comes to the exam time, okay? Anyways, that'll do it for today. I'm sorry to keep you a little bit past. If you have any questions, feel free to email me. Otherwise, I will see you guys on Wednesday for the quiz and the rest of the lecture. All right.